Everyone. Today I wanted to talk a little bit about graphs. Okay, so graphs are a really common type of interview problem, and you'll run into them all over the place. And often what you'll have to do is kind of implement your own graph in order to represent whatever's going on in the problem. There's a lot of different ways to actually represent a graph, and it really depends on what kind of problem you're trying to solve. Sometimes it's helpful to just hold all the nodes in memory with references to each other so you can keep track of what all the different nodes are and where the references are, and so you can traverse them in a certain order. Other times, it's very useful to just keep track of a list of what nodes are connected and what nodes there are, and then traverse that list by just iterating over it, and then making some some algorithm that's based on that. But again, it really depends on what is it that you're trying to solve. So let's talk about how to represent a graph in one of the ways. So the thing that I like to do is to think about graphs we've already actually seen. So we've seen graphs like this before. This is a, I haven't written this, the notation here like this, right? But this is really what we're dealing with here. This is called a DAG, a directed acyclic graph, as in all the edges, all the arrows connecting one node to another have a direction. 10 is connected to 8. 8 is not necessarily connected to 10. You can't get to 10 from 8, but you can get to 8 from 10. So there's that. And then it's acyclic, as in there's no cycle. We don't have anything, like this going on, right? If we had this would become a cyclic graph. Or really it would be more like if you added these two connections, then we could go in a circle. And so that's what a cyclic graph is. So this graph is acyclic, which means, all these little pieces here that I drew aren't going to affect our graph. And it is a graph because what we've got is nodes, right? These are nodes. And these are edges. So nodes and edges is really all we need in order for something to be a graph, right? And so in that case, what we need to do is create a class. Node, right? And so just like all of our other graphs, linked lists, trees, we create a node and we define a init function, which takes in self and some data. Right? Now, once we set up our self.data with data, we have a fully functioning node, but we can't connect it to anything. And so what I like to do here is define a function called something like add directed edge. And pass in self and the node, right? And so in order to add a directed edge, that means that the reference from one node is going in one direction to another node. So self.edges equals or dot append node will create a directed edge, right? So self.edges being a list, appending that node to that list basically creates a connection from our initial node to this other node. You can't go back. And so if you're right now, basically, if I were to say, node 1 is a node and it is of 1, and then node 2 is a node and it has 2 in it. And if I say node 1 dot add directed edge of node, that's essentially similar to having a linked list. I've only got the one next. And so then if I wanted to traverse this, all I would do is visit every element in self.edges, right? And so right now, our graph actually looks like this, right? We've got 1. And then if this is a list of edges, then we've got 2. and this first edge points here. It's a reference to 2. So it's very similar to our linked list that we've seen. And so the thing that makes this a graph, though, rather than a linked list, a linked list is a graph, but the thing that makes this more of a less constrained graph, right, is the fact that it doesn't actually have to be a directed edge, right? Def add undirected edge self node, right? And so if we wanted to add two edges, then we could say self.edges.append node and node.edges.append node. And so then if I change this to undirected edge, right, then our node 1 and our node 2 both have a reference to each other. So add directed edge really does something like this. First it adds that first one, and then it adds another one here, like that. So, if you think about that in like graph notation, what we have is 1, and then we go over here, and we have a 2, and then 2 is also connected to 1. So this is it's still a directed graph because we kind of have to add both edges simultaneously. But because we've ensured that there is a connection, we could kind of imagine that this is an undirected graph. 1 and 2 are connected, so this is cyclical, right? We could never loop through all the children and kind of come to the end where we're going to hit a none. We're never going to hit a leaf node here. So this is a cyclic graph. So as you can see, what we're really doing is just breaking some of the rules of trees and linked lists, right? By storing a list of edges instead of a single edge or right or left. But because of that, that makes graphs a little bit more tricky to traverse, and it makes it a little bit more tricky to do things like figure out the depth and stuff like that. That said, graphs are very useful for a lot of different things, and so we'll get into that in the next video.